Welcome back, everybody. We are now kind of nearing the end of our webinar series. I'm hoping that, yes, there we go. So we're nearing the end of our webinar series now, but we will have a bonus couple of webinars towards the end, so stay tuned for those ones. One of them I can announce is going to be the Skypool webinar. So I don't know if you've seen in the media press recently, but the Skypool was kind of is the building 10 floors up. It's the crystal clear acrylic. So just Google it, you'll be wowed, and then you'll really want to join us. And hopefully we're going to set that date for the 20th, but that's to be confirmed. So watch this space for that one. Today's webinar is on the H.B. Allen Centre, the Keble College, Oxford. And it's the building that appeared to float. It's a really interesting project, which we did, which we finished a couple of years ago, well, last year, I think it was. So it's a super interesting project. And the people who are going to take us through it this week are Toby Ronald, who is our structural director, and Max Chalet, who is our senior director, senior structural engineer, sorry. I just elevated you there, Max. Sorry about that. They're going to take you through that. Just a couple of things before we start, as always. If you're new to this, though, there is a chat questions function kind of over on the right-hand side of your screen. So if you've got any chatting things, then you can kind of give us a little word, say hello. And if you've got any questions, then just pop those questions in there. It's always nice to hear from you guys. I think I've enabled emojis, so feel free to send us hearts. It's new. It's a new function. Try it out. Okay, then. Right, I'm going to hand over to Toby, and I'll let him take it away. Thanks very much, guys. I'll see you later on.
Good. Thank you, Kat, and thank you everyone for coming and listening to me and Max talk about our project for Keble College, the H.B. Allen Centre. So we've done a number of projects in Oxford over the years, both for the university and for the respective colleges. And this project on the Acland site is located just north of the Keble College itself, just for those of you that know Oxford, between Banbury Road and Woodstock Road, circled up there, the B3 on the map. We're going to talk about engineering today, I think. So we haven't got a whole suite of finished architectural shots, but here's the kind of the main shot, which is the main quad of the project. Jesse, one of the architects from Mica, I think is there wandering across the quad as part of the photo shoot. And in the middle of the image there is Acland House. That is one of the things that we're going to talk about today. The building is really a graduate accommodation building on the upper level, so 3 floors of graduate accommodation around this central quad. The ground floor levels are kind of mix of social and a kind of mixed-use spaces, and we'll talk a little bit in the context of Acland House. There's a big basement under both the quad and the whole development that houses some kind of commercial ventures and some collaborations between the college and industry. We're going to talk mainly about the kind of buildings and features of the buildings in the main quad, but as part of the development, there's also a slightly separate building. This building, the Woodstock Road building, which is another nice piece of architecture and engineering too. So, in structural engineering terms, the building is made predominantly out of reinforced concrete. The upper levels are flat plate, conventionally reinforced concrete slabs, supported on blade columns that sit in between the student rooms on the upper levels. It has a steel frame roof structure over the top and a big basement that we'll look at over the whole development, but ultimately sits on a raft foundation. In the middle there, in the yellow block, is Acland House that we're going to get onto. So I think for us as engineers, this was kind of really the defining photo from the project, a kind of really dramatic moment, which signified both the kind of I guess to some degree, the kind of conclusion of the kind of enabling works of the project, and the beginnings of permanent construction coming up out of the ground. But it's obviously also a dynamic image in itself. So this is one of the things that Max and I are going to talk to you about today. We don't have time to talk about the whole project, but we're going to talk about 3 bits that kind of build a little bit, I guess, on the title that Kat gave us in terms of kind of floating structures. It wouldn't be right to talk about this project without talking about some of the many collaborators involved in developing a project like this. Micah, the architect, Keble College and everyone at Keble College who helped deliver this over the years. I think forgot the kind of pandemic year that's kind of gone by quite quickly. So it actually finished a couple of years ago now, and it's in full use by the college. And then because we're going to talk a little bit about the kind of construction and about temporary works, a kind of special mention to the main contractor BAM and their temporary works designer Locking and Clark, who were heavily involved in some of the things that we'll talk about today. So Acland House, which we see here on a kind of grey early site visit day, was built in 1895, I think. I'm not an expert about the history. And as part of the Sarah Acland nursing home, was one of the UK's first purpose-built hospitals, and hence the kind of importance of keeping it in the finished project. Actually, in the image that we look at now, actually the only 2/3 of the main villa are actually original fabric, and the third on the right is actually a later addition. But as a part of the project, we demolished the clearly non-original wing on the right, and the wing on the left actually is original, but we were able to take that down and replace that with the new building, but we kept the main villa. So here's one of Micah's rendered 3Ds that kind of captures, I think, the vision of the project in many ways. So you can see one of the main moves that happened in making the project viable, really, is putting this big basement under the whole extent of under the new building, under the quad in the middle, and also completely through underneath Acland House. And by doing so, it obviously added lettable space for the college that helped with the commercial viability and the funding streams for the project. But from an engineering point of view, we were also supportive of that. Acland House had its own basement, a kind of small, shallower basement typical of Victorian construction. But by putting it on one big unified basement, it posed us the challenge of how you hold that up. But we liked it from an engineering point of view, because by putting Acland House on the same foundation system, on the same basement box as the big new proposed development, it meant that ultimately they would all move together, and we wouldn't have to deal with differential movements between the existing building and the proposed. And also from a waterproofing point of view, from the basement, enables us to have a unified wrapped waterproofing system around the whole basement, which we liked. So getting into some of the kind of temporary works schemes that made that image that we looked at possible. And the first kind of move is putting a transverse slab at ground floor level under Acland House. And that transverse slab, which is ultimately a reinforced concrete slab, has 2 functions. It works in the temporary case, in the image on the left, in supporting the walls that you can see shaded of Acland House off temporary piles, which are the little orange pink dots on the left. And then that same slab also then works in a permanent case in supporting Acland House walls off the new permanent structure, which is shown in blue, which are the walls underneath. And for reasons of basement layouts and things, they don't perfectly align with the walls above, and therefore the transverse slab works in a permanent case and is still working today to transfer the loads of Acland House. On the left-hand image, you can also see the bigger round dots, which are larger piles that are part of the contiguous piled wall that are part of the basement box. And they were used to help stabilize stabilise Acland House in the temporary case. So they provide the lateral stability to the transverse slab that you'll see why that's required as we look through the excavation photos. So we've got a few construction shots of BAM subcontractor team at work. On the left here, clearing out Acland House, and on the right, with a Minipile rig feeding in between the walls and the doorways and the corridors of Acland House to install piles. And if we go back to the piling layout, you can see that the piles are positioned purposefully in locations where the Minipile rig and BAM's piling team could get access. The transverse slab, in order to hold up Acland House, this transverse slab needs to feed through the walls of the brickwork walls of Acland House and hold them up. And to do this, the scheme used pinford stools, designed by Locking and Clark here. Each stool consists of 4 circular tubes with a plate top and bottom. And little localized hit and miss pockets are cut out of the brickwork, and these stools are inserted. And they're packed top and bottom, and the loads then from Acland House transfer down through the stools, in this case, at the minute, through into the foundations below. You can see in the foreground of the image the temporary Minipile sticking up onto the ground. And by doing this, transferring those loads from Acland House through these stools, that then enables the brickwork in between them to be demolished. And so there was a time in the project when Acland House is purely sitting on these stools, which then bear down onto the existing strip foundations in the existing basement below. We'll just flick through these, and this is then reinforcement fed through the stools, and ultimately the concrete's poured through. And the purpose of having these stools with 4 little legs rather than being a solid block is to allow that rebar and to allow that concrete to flow underneath the walls of Acland House. So here's the rebar, another image going in, the rebar being designed for those 2 conditions, for the temporary case in transferring the load to the piles, and the permanent case transferring the load of Acland House to the permanent structure below. BAM then chose to pour that transverse slab in 3 parts. And here it is, Acland House sitting on the transverse slab onto the temporary piles, but BAM haven't commenced the excavation. And then there's the remaining basement construction. You can see on the left there, it's raft foundation, concrete piles and whatever gradually progress towards Acland House, temporary works in Acland House being completed and excavation beginning underneath. During this and before excavation commenced, we did a little bit of stabilizing of Acland House. Windows were blocked up. There's some localized propping went in around the staircase within it, just to give it a little bit more rigidity to act as a block during the work. But in reality, it moved very little during all of this process. And then Locking and Clark chose to temporarily stabilize the Minipile. So after half of the excavation commenced, these temporary props that you can see in kind of blue-grey went in. And then the excavation continued. And that kind of led to this moment in the project that certainly got us excited about. So here, completely held up, sitting on its transverse slab, as the basement construction continued around it. You can see the contiguous piled wall in the foreground here, beginnings of the concrete core and one of the concrete cores in the background. And so gradually that concrete construction came up and got built around Acland House. And eventually that led to the completion of the ground floor slab and the pouring of the walls underneath Acland House. And at that point, the loads of Acland House were able to be transferred onto the permanent structure, onto the walls below, onto the raft foundation, and ultimately loaded down onto the ground. And at that point, BAM were able to take out the Minipiles, and they're removed from the project, and the loads then transferred fully onto the permanent system. And there you go, back as it were, kind of unmoved, and despite being there for pretty much 120 years now, the building kind of having gone through quite an exciting period of 2 years of its life. So I'm going to hand over to Max to talk about two other bits of the structure that are doing similarly, I think, kind of fairly unique kind of structural things.
Yeah, thanks, Toby. Yeah, so obviously Keble was essentially the key items of the project, but there were several others structural elements which were noticeable and quite interesting to detail a bit. So the first of those two is essentially those kind of shift in arrangement between the student accommodation on the higher floor, which were like highly compartmented and fragmented, to the ground floor, where here obviously the goal was to have like kind of large open spaces with no internal support. So you can actually see that quite clearly on that photo, either side of Acland House, and on the right hand side, the east wing, where we've got the cafe and all the common area. So if we look at that in a bit more detail, so that's essentially how it looks like now. So we've got column obviously along the facade in both north and south alignments, and nothing in between. At the floor above, we had previously those kind of shear walls that cross entirely transversely the building on those kind of key locations, and we were keen to try to use them in order to form a transfer structure. The only key issue here was that the central corridor that essentially provide access to all the rooms is right in the middle of the building and split that wall, which obviously complicated a bit the task about making that working as a transfer structure. So eventually we didn't give up and trying to make it work, which end up to preliminary something like that, when you've got your walls at the upper floor, which sits on a set of column at the ground floor. So there were many challenges to overcome in order to make that work. Obviously, the first one was linked to the kind of asymmetrical properties of the system, where you've got only one column on the south side, but two columns on the north side, which will essentially tend to twist the system and making the south wall leaning against the north one. So that's kind of the things you can see in the early study we did here. So you have the plot screen, analysis plot on the left-hand side, which shows that, where you see actually that wall leaning against the other one, creating a lot of residual bending moment into the slab on top of all the membrane forces that will have to be transferred. And also the fact that that kind of back column is, or the stiffness of that back column is quite key in order to fine-tune the behavior of the system. So that was essentially the first step, trying to understand this, refine the design to make sure that we have something which is well balanced under just permanent gravity loads, which we eventually managed to do, which obviously in the same time was having kind of a beneficial effect on those kind of vertical displacement. The second challenge to overcome was kind of linked to the lateral stability, because obviously here you can see that there's a clear breach in terms of continuity. So obviously here it was quite to using other lines of stability, which were hopefully either side of those areas where we've got our lift shaft and other shear walls. So essentially keep using the slab as a diaphragm and transferring membrane forces to those locations. And eventually, one of the last key problem which we had to solve was linked to the disproportional collapse. So obviously we had like many design methodology in place to deal with that. For the more typical RC frame was pretty straightforward, because just by providing horizontal and vertical ties will actually satisfy building requirements. But when we've got to those elements with the twin flag wall system and some of the transfer slab, we had to do like more in-depth analysis to make sure that things perform as planned, as expected. So there is actually, when we talk about disproportional collapse to that particular system of the twin walls, I think there is a couple of interesting to flag here, is that the problem can be pretty much split into two main areas. The first one is kind of the risk, the exposure of each column to any accidental situation. So along, I don't know if you've seen that on the previous shot that we shown, but along the north of the site, there is kind of an access road where you've got traffic, potentially trucks. So obviously that kind of column along that road was like more susceptible of of to disproportional collapse than the two other ones, and there is kind of that asymmetrical risk exposure in between those columns. And the second aspect was the fact that the kind of robustness of the system will be different depending on which column should be removed, accidentally removed. So obviously, in that case, the south corner was the most critical one, because here the redundancy is less great than what you can have on the north. Mainly because here, if you lose the column number 1, you have only like one preferential way of redistributing your forces by making the slab working in the east-west direction as a continuity between the shear wall and the column, while on the north you still maintain pretty much that kind of twin flag wall system intact and still performing. And eventually it was about trying to develop with BAM a suitable method segment for the construction, because obviously that whole system works fine when the third slab is completed, but before it has to be probably propped. So we end up with that solution of having like a temporary horizontal link at the top of the wall in order to act as a substitute for the concrete slab, waiting for her to cure and be ready and be strong enough to take those loads. So that on top of all the temporary propping we had to keep until the completion of the third floor slab. The kind of second element of interest on the project was the steel staircase, which were located in on the 3 main corners of the building, serving the student accommodation. So those kind of cantilevering scissor staircase are a key signature of Mica, and they already implemented those in a couple of other projects in the past. So again, we are quite keen of getting something kind of architectural and kind of cleaned visually. So those staircases are made of thin plate only, for everything, for stringer, half landing, goings, and risers. And they're essentially working as a monolithic piece from slab to slab, where they are connected. So you can see that there is literally no connection whatsoever. You can see it's very simple and very clear as a structure. And what is quite nice about them, I think, is that they're located in the internal corner, the 3 internal corner of the main building, and they all have kind of a narrow window that runs all the way up, and making them visible from the central courtyard, from pretty much like, any kind of central position. You can see all of them from one single position, which is actually quite nice, I think. And then that's pretty much how it looks like. So the idea was to essentially build, lift, and install those kind of floor-to-floor staircase element in one go. So we had kind of a quite long process of iteration with BAM and subcontractors in order to develop a suitable method construction, and especially connection to the slab. So as you can see here, the solution we ended with connected the threads and going through a cast-in plate, which were itself like cast with the concrete through rebars welded at the back of it. That solution obviously was quite satisfactory, because it was relatively easy to build, easy to implement within the formwork, and level up properly. It also gave tolerances or maximum flexibility during the installation, as all the bolts holes were drilled and tapped on site directly, and also gave us the opportunity to include that kind of little steel block, which will be useful for installation, acting as a temporary propping, and also diminishing the amount of temporary props we will have to get into that relatively narrow space. Another thing which is interesting is actually how it works, because it's maybe seems to be straightforward, but it quite isn't. The fact is that if you remember what I've previously shown here, is that you will be tempted to use your stringer as your cantilevering beam to support your structure, but your stringer is connected at its bottom, and the top is pretty much free or unrestrained in and out of plane. So on the three stringer you have, which are the two side stringer and the central wall, only the central wall can actually work as a cantilevering piece, as it has 2 connection points to the slab, while the side stringer cannot really do that. So in order to make it work, we'll have to be propped at some point. And how we have achieved that essentially is by using the risers with some reinforcement with SHS embedded into the half landing to essentially provide some sort of support to the side stringer and bring the load back to the central one. So you essentially end up with something like that, when you have the side stringer having like an intermediate support here, and the central one not really supporting the half landing, but I mean through that kind of interface being here helps to support the side stringer with on the central one at the end. So that resolved quite nicely, and also helped to deal with all sorts of asymmetric loading or horizontal load that inevitably put some torsion into your system. So in that case, you can work with your side stringers that actually can deal with that. And eventually, yeah, it was all the analysis of the serviceability performance of the staircase, as we had like relatively sometimes like great span without really any connection to any support to anything. But hopefully all of that was satisfactory. So checking the natural frequency, and later on the response factor and acceleration. So here, pretty straightforward result when you can see that the worst result are obtained at the end of the cantilever, which is kind of expected. And we had the possibility to kind of roughly check that serviceability behavior later on, just after the completion, and it was just working as we expected. So that's pretty much for the project. I just leave you maybe with a little quote that I find quite good in the context, which is from Barack Obama on when he was talking like 5 years ago about some new national monuments opening ceremony, when he said, but part of what we're preserving here is it's also history. It's also understanding that places that look ordinary are nothing but extraordinary. The places you live are extraordinaries, which means you can be extraordinary yourself. Thank you very much.
Thank you, guys. That's really fantastic. It's great to hear about the engineering, the structural engineering this time round. We've done a lot of kind of on glass and facades, but actually good old actual structural engineering is really exciting to hear about. How many, I'll kick off with one question first. Toby, how many sleepless nights were there when they depropped? That must have been quite a nerve-wracking kind of thing to do. Or were you cool as a cucumber? Or were you just kind of like, you knew what was going to work, it was going to be fine? I suppose that sort of ties into Duncan's question. He's asked, how did your comparison of your predicted movements compare with your actual records? So I suppose that sort of ties into it.
Yeah, I think not many sleepless nights really, Kat. I think that's broadly a reflection of the Pinford method being very successful in kind of avoiding the drama. I think that you get in quite a lot of temporary work solutions where you transfer the load from one position to another position. So, compared to alternative options that might include needling through the wall, and you're putting kind of transfer beams through to help hold something up, there's always a kind of, a transfer of load, and that transfer of load, comes with a kind of movement effectively. So, I think one thing that's very nice about the Pinford stall method, and why it's generally used, I mean, it comes from a kind of use of underpinning, really, it's mainly used in underpinning, but is that you keep the load going in the same path, and therefore things don't move. We ended up in a permanent condition where there is a transverse slab and it does move the load. But broadly speaking, the walls are aligned as best as they can to the loads above. So the final position is relatively stiff in terms of that transverse structure.
Yeah.
And in putting in quite a lot of temporary work, mini piles, that piled foundation in a temporary case is quite stiff. So really the only movement that Acland House has kind of ever seen, well, I guess there's three movements. There's a it's actually when you put in the stools and you pack them tight, you pack them so that they take loads, and you do that by pushing Acland House up just a little bit. And then there's a little bit of deflection of that transverse slab, but not a lot. And then it has seen kind of gradual settlement of Acland House with the gradual settlement of the half foundation. But that's all been consistent between Acland House and the new build next to it. So the whole development, has inevitably settled onto its raft foundation. So it's all moved together. So effectively, that movement is kind of, it's a real movement, but in terms of relative movement to anything around it, it's not moving. So I think the kind of, broadly speaking, lack of movement of the whole thing kind of takes away that kind of like the kind of anxiety that you were maybe kind of suggesting.
I've got full faith in you, Toby. Obviously, I've got full faith in you. I think I wouldn't have had full faith in myself if I was that engineer. I
don't know whether David Allen and his team at Lucking and Clark had more sleepless nights than we did, but I think broadly it was a relatively low stress kind of situation.
Yeah. I was wondering whether or not when the piles were designed, were they designed for sort of digger impact because obviously you're digging a basement in and around the piles which are now exposed, and then also sort of when you expose the piles, was there a consideration around the fact they might buckle, given if you're exposing the piles, then they become sort of more at risk of buckling. So were there any kind of additional things that you then had to do to make sure that they didn't?
Yeah, ultimately those mini piles are designed as columns. They have reinforcement cages within them, and they're designed as columns that act over their unbraced height. The reason for the temporary bracing that got put in at mid-height is to reduce their buckling length and to reduce the kind of size and reinforcement requirement in them. But and that was also part of the reason of tying it back temporarily to the big contiguous piled wall around the development, is that just stabilizes the top of them.
Yeah. And in terms of the digger impact?
Sorry, I didn't hear your digger question.
what was it designed against digger impact, or was there kind of more of a plan on site that meant that kind of that would never happen?
I don't think it was designed for a digger impact, no. I mean, Bauman and the team were very careful in digging out around.
Oh, absolutely. You can either design it for that, or you can design it for the site for kind of working around that, can't you? So,
but there's quite a lot of redundancy. I mean, there are a lot of piles underneath that in order to control the movements and to be confident about what's going on. But nothing major would have happened if one of those piles got knocked down.
No, there's redundancy in it. Sounds good. James is asking, probably a question for Max. Did you think to use the handrail to help resolve the forces in the stairs?
No, never. No, because the handrail was pretty much architectural only, and it wasn't actually needed at all. Although
Go on, Max. I was going to interject.
Although at the end it served a purpose that we didn't anticipate it for it, but that was quite helpful, is that when I've mentioned previously that we did some kind of post-installation testing on the serviceability behavior, on the dynamic behavior of the staircase, we did, and the only thing we noticed, which was a bit weird, is that if you were like trying to rush down the stairs at the highest speeds you could make the end of the stringer at the top flap a bit. because of like all the vibration ending up there. So when you previously, when you didn't have the handrail, you had that behavior, but after when they installed the handrail, which was obviously like continuous and joined with the balustrade, it actually kind of provides some sort of restraint to that end, that free end, that essentially solved that. So that was a good thing at the end. But yeah, the stringer on itself was the thing that provide that provide the lateral stability and support for the staircase itself.
Super. Pete Matcham has asked about going back over onto Acland House, kind of jumping backwards again, but sort of did you have any movement sensors on the existing building to monitor it while it was floating? Did you get any alerts from it? He says it's a remarkable project. Congratulations, which is a nice thing to hear. Thanks, Pete.
Thanks, Pete. Yeah, of course, Acland House was rigged with movement monitoring sensors throughout, both before work started in order to get base level readings, and then throughout the whole operation up until the ground floor was poured. I can't say that we didn't get any alerts, because actually I can't quite recall, but there weren't any of really that triggered by excessive movements. Whenever you put any kind of movement sensors on buildings, I mean, they expand and contract daily in terms of temperature fluctuations and the like. So I'm sure we had some alerts at some point, but the movements generally, I mean, were all under 5 mil for sure in terms of general movement. So Acland House actually remained very well protected throughout.
Yeah, if I recall correctly, we had 2 alerts throughout the whole project. Once was when they were doing some work on Mickey Lane, so just right at the back of Acland House. And the second time was when they removed the sensor but forget to bring the link with the alert system. So no, pretty much no alert at all. Yeah,
that's fantastic. I think that probably reflects the calmness. Probably reflects in the comment that we've got from Roger Bowden, who the client's just on the chat function, which is great. Mm-hmm. And he said how brilliant our team was. So congratulations, guys. That's nice feedback from our client, which is great. He says the results are quite extraordinary. I think that was kind of one of the things which I was going to ask, actually, was have you had any feedback from anybody who's actually using it in terms of kind of sort of what's performed well and what hasn't, or what has performed well, hopefully, fingers crossed.
Yeah, I haven't, Kat. I mean, I haven't been back since the opening ceremony, but
that's I suppose COVID's put a stump all over that. So
it has in the last year, yeah.
Tricky, yes, exactly.
I think it's still standing.
Oh dear. Now I was going to ask about the heritage architects and allowing the demolition of the original wing, and what were the kind of discussions like on sort of the demolition things, but I think Roger has answered that. What were your views from that one, Toby?
Roger knows much better than me about the planning debates that surrounded which part of Acland House we had to retain. Yeah.
Absolutely. Okay. And so what things, what were your learnings taking forward? Have you used this kind of stuff on any of the other designs that you've done later on after this?
Yeah, I mean, the general temporary works approach is very similar to an approach that we've used quite successfully at the Victoria and Albert Museum, which, I mean, maybe that's a subject for another webinar, but we removed an awful lot of load wall out of the Victoria and Albert Museum and kept the British galleries in operation above. So in about 2 foot above where we were demolishing walls there was a kind of priceless China collection still connected to the wall. A different version, we different detailing for sure, that we were putting steel frames in there, but the same kind of principle of keeping the load directly down the wall worked very successfully at the Victoria and Albert Museum.
Absolutely. How about you, Max? How's it sort of developed your things for going forward in future engineering?
Well, actually, that was my first project when I arrived to the UK, so it was like a fast track to improve a lot of things. My English first, but all my knowledge of UK markets, UK stage of construction and everything. And I was also on site, working with BAM. So yeah, I mean, the change he has made for me is like countless in terms of I cannot spell out something specific, but yeah, obviously he has had a major influence.
Wow.
On a lot of things, actually. Yeah.
That's a bit of a baptism of fire, isn't it? Having this as your first project when you come to the UK, that's an interesting one to kind of kickstart you off, isn't it? So
yeah, no, it was a really good project to start, I have to say. Yeah.
Yeah, absolutely. Well, on that note, I think we might wrap up. I think if nobody else has any more questions to ask, we'll wrap up this one and keep it a nice short webinar for anybody wanting to watch back. But yeah, I think we'll wrap up. So super. In which case, then, all that's left for me to say is watch out for the coming webinars in the future. Hopefully, we're going to have one on the Sky Pool coming up, I think on the 20th, but that's to be confirmed, so watch this space. And we're going to take a week's break now because of the bank holiday, and then we'll come back on the 12th of May for rehabilitation of Parisian facades. And that one is actually going to be in French. So anybody wanting to test out their French, then welcome back for that one. That's going to be carried out by our Paris office. And so brilliant. Have an absolutely fantastic evening, everybody. I'm just making sure that nobody else is going to come in with the last minute things. Nope. Super. Thank you very much indeed for joining us all. I hope you all have a lovely evening. Join us back on the 12th and then on the 20th, and then we'll see what we do after that. Great. Thank you very much indeed, guys. Take care. Good night.
Bye.
Thank you. Bye-bye.